Thank you very much. It's really a great pleasure for me to be here. This is my first trip to Bulgaria. I have heard so much about INSAIT, and it's fantastic to see it with my own eyes. I think this is such a great opportunity for Bulgaria, and it can really lead to a transformational change in what's happening here in education and business, and I'm very pleased that in the future I'll be able to take part in this, and I hope to get to know many of you then. So in this talk, I will be talking about research in automated reasoning for security protocols. I'll actually focus on protocols for banking, although I would like to say a little bit about Anapaya and a subtopic of this talk. The subtopic is, there's nothing as practical as a good theory. So in this talk, I'll be talking about foundations, and I'll apply those foundations to banking, but one can also apply them to banking protocols, but one can also apply them to network protocols. And I'll just say a little bit about that. Together with two other colleagues at ETH Zurich, over the last 10 years or so, we've been researching how to build secure networking protocols. And after about 6 years of research, we felt we understood the theory well enough that we formed a spin-off, Anapaya Systems. Maybe I'll point here, it's easier. We formed a spin-off, Anapaya Systems. And Anapaya Systems is building a new network, fundamentally different from the internet. The internet isn't built with security in mind, and it's completely insecure. You have no control over where your packets go. It's not transparent where your packets go. Certain things are completely impossible. For example, for those of you who know about inter-domain routing across autonomous systems, it's impossible to achieve things like inter-domain quality of service. The internet suffers from fundamental problems. For example, there are hijacking attacks using BGP that make it possible that when you're doing banking here in Bulgaria with your bank, that your packets flow over America or over Russia. In any case, we've built a new approach to the internet, new security protocols that solve all of these problems. And about 6 years ago, 5.5 years ago, we founded a spin-off, Anapaya. And it really illustrates this point. Sometimes nothing as practical as a good theory. We started with theory, and we started building this network and exploring what could be done in practice. Today, you can use the Scion Internet, which is provided, the industrial strength version is provided by Anapaya Systems anywhere in Switzerland. We have full coverage in the Swiss market. Over the last few years, the entire banking industry has moved from a closed network that they were using called Finance IP Network to using this open internet standard, Anapaya System, using routers provided by partners in our partner ecosystem such as Sunrise and Swisscom and other ISPs in Switzerland. So this is really something that, for me, I'm very happy about, going from a research idea to something where we're talking about around 3 million transactions a day, manipulating over 170 billion in Swiss franc. The success of the Secure Swiss Financial Network has led to new plans for expansion. The entire healthcare sector in Switzerland will be moving over to Scion because doctors and hospitals and pharmacies share very sensitive information. And the great thing within Scion is you can ensure that that information stays within Switzerland. Scion is now used extensively for research and education. It's been used by different ministries in Switzerland. For example, Arma Swiss uses it. Some foreign ministries have used it in the past, and I think this will be expanding. And I guess the point I want to drive home about this is that really often nothing is as practical as a good theory. The underlying theory behind Scion is thinking very deeply about computer networks and how to improve change and improve the fundamental algorithms being used, and then doing so in a verifiable way such that we can build an internet where we can make verifiable claims about its security. My focus in this talk will be on the verification part, but many of the messages that I will have about verification directly carry over to this particular use case. The focus here, though, will not be on the new internet, but I'd be very happy to talk about that on my next visit. But my focus will be on payments and verification technology. I think payments are something perhaps even more approachable to a wide audience because you're all doing payments. I mean, payments with credit cards like this, with Visa, American Express, etc. And I will talk about the use of verification technology, the technology we use to develop this new internet, but to payment networks. Now, I realize that not everybody here has studied security, so don't get scared. I don't expect you to understand this. This is part of something called the Internet Key Exchange Protocol, just part of it, and it's used to build VPNs. And without going into too many details, what's happening here is some different keys are being derived, and they're being used for different keyed hashes. Think message authentication codes, or MACs, if you know what those are. And also certain data is being signed, and this is all being used to exchange keys. Now, even without knowing what's going on, you might ask yourself certain questions. You might say, is it necessary to have all of these keyed hashes? And if you ask a typical internet engineer, they'll say, oh yes, we design protocols following principles that you should use different keys for different purposes. And you might notice, for example, that certain arguments on certain positions change, and you might say, does the order of arguments matter when I design an internet protocol? People will say, oh yes, it's good to swap around things because it makes it harder to have replay attacks. My point, though, is these are completely the wrong questions to be asking. When you design a security protocol, or when you design any system whatsoever, you should be asking, what are its key properties? And in the case of security, you want these properties to hold in an adversarial environment where an adversary is trying to attack it, so you can ask yourself, what are also the properties of the adversary? And once you've answered those questions, there's another important question. Well, how would I prove that my protocol really does what it should? But that's not what happens. What happens is these other types of questions are asked, but not typically the important ones. Said another way, the design of security protocols, and indeed the design of much of our software, is approached as an art. So for protocols, you have best practices. I gave you a couple of them. You have design by committees. You try to reuse previous protocols. And the situation reminds me of the following quote. Let me read it with you. Whenever I made a roast, so that's a big piece of meat, I started by cutting off the ends, just like my grandmother did. Someone once asked me why I did it, and I realized I had no idea. It had never occurred to me to wonder. It was just the way things were done. Eventually, I asked my grandmother, why do you always cut the ends off of the roast? And she answered, because my pan is small, and otherwise the roast would not fit. So this is the way we're building security protocols and software systems. We're using best practices somehow delivered over the generations without really understanding them necessarily, and without really knowing if they will achieve the ends that we expect. I'd like to contrast protocol design as an art with design as a science. And here I mean science in the root sense of the word. So the discovery and knowledge of something that you can demonstrate, and in particular verify, within an appropriate community. So this means rather than designing systems, protocols, or other types of programs and testing them a bit and debugging them a bit and kicking the tires a bit, how can you put this on a firm mathematical ground where you can make provable statements about the security or other properties of your systems? And my thesis here is that formal methods in automated reasoning, which is an INSAIT, these are important topics in INSAIT, are the right way to do this. You can specify what your system does, what the adversarial environment does, what properties you want. And then you can use these tools to produce proofs, to explore alternatives, and perhaps to understand when the proofs fail because there are attacks. And that'll be part of the topic today, looking at credit cards. And when things fail, things really fail. Okay? I've been working for about, since 1997 on techniques for doing this. My gosh, tempus fugit. And the tools now have gone from early experimental tools where we work out the mathematical theory to tools that can and are being applied by all of the major companies you might think about today, from Amazons to Apples to Googles, etc. They are using these tools to help build a more secure world, a more secure IT infrastructures. And I give some examples of where Tamarin, my tool, has been applied. It's been applied to 5G, which is driving telecommunications, to TLS 1.3, which you're using for banking and software upgrades, for EMV, which I'll talk about, for Scion, which I alluded to. And these companies are becoming, slowly but surely, tool users, and I'll talk about that a bit at the end. This problem isn't an easy problem But it's a fundamental problem in computer science. You have a system, and you'd like to show that it has certain properties, in security properties. So the system specification explains how the system should operate. And by the way, this isn't so easy to give a specification, because in practice, if you look at requirement documents and design documents, they're incomplete and ambiguous. So part of the work in verification is to first make things precise, and only once they're precise, you can make things formal. And of course, if things aren't precise, how are you going to implement them, right? But people do. Next, you have to specify what the adversarial environment is, and this is often unclear. If I design some system and I say data is it secure against a network adversary? Is it secure against an adversary who has physical access to my disk, my computer, and can take the disk out and forensically analyze it? A solution may be secure in one setting but not another setting. So for security, you must specify what the adversary is. Then the next question is, what properties should my system be, should my property achieve? You'd be amazed if you ask most developers, what properties does your system achieve? They're not always sure. In the case of security, this is difficult because even if you say, well, I should somehow authenticate participants, it's not completely clear, it's ambiguous what authentication means. Now, finally, once you can make all of this precise and spell it out in a formal language, you then have the question of how do you construct proofs. And in general, even for very simple properties, these questions are undecidable. Undecidable doesn't mean that I can't decide it or you can't decide it. Undecidable means there is no algorithmic solution where an algorithm can always say yes or no, this protocol is secure or not. And even in restricted cases, the problem can be very, very difficult. So in my group, we've been developing for this particular tool, Tamarin, for about a decade, working on the mathematical foundations, which are based on symbolic reasoning and constraint solving, and the methods and the tools associated with it. So Tamarin is a constraint solver for basically trying to figure out how an adversary can attack a protocol. And on top of this constraint solver, we built a theorem prover. And the theorem prover will ensure that it's not just this attack or that attack cannot work, but that no possible attack can work. And if there is an attack, it will find it. I will give you a brief crash course. For those of you, I think there's some people in high school, this might be a little bit challenging because I'll need to talk about things like transition systems and formal logic, which are the foundations of computer science. But this will be fairly brief, and I'll try and keep it at a high level. Okay, so Tamarin is a theorem prover of a certain type that's also sometimes called a model checker, because you have a description of the system, which is sometimes called the model because it's a mathematical model of the system, and you have a property, what the system should achieve, and you give both to the tool, and in the case of Tamarin, it turns both of them into constraints. It negates the property so that the property expresses something good, the negation is something bad, like an attack, and then uses a dedicated constraint solver to try and find behaviors that are consistent with both the specification and the negated property. That's a behavior of the system that's bad, i.e. an attack. Now, if it can find that, it gives it to you in a form such that you have an attack on your system, and for example, in the case of credit cards, let me get my prop, you can actually try the attack out. So when I say, and then we found an attack, I mean Tamarin's constraint solver found an attack on a credit card. So that's what we'll be seeing later. Alternatively, it might be the case that there are no attacks. And no attacks means not just we tried this attack or that attack, but it can construct a proof that no matter what the adversary does, no matter how protocol runs are interleaved, there cannot be an attack on this protocol. So despite being an undecidable problem, very often it's successful. But since the problem is undecidable, sometimes you might run out of time or memory or patience. And then one can work with Tamarin, for example, providing hints. For those of you who've studied program invariants, you specify certain types of invariants. And those are often enough to make the proof go through, if it's provable. So very briefly, how might that look? So we need to specify three things: a model of the protocol, what the adversary can do, and properties. So we model the protocol using a certain type of rewrite rule called multi-set rewriting. And the multi-set rewriting rules give rise to a specification of a transition system. Who here has seen transition systems? So a couple people have. So if you've done anything, for example, like, well, basically automata, basic automata are transition systems, the finite automata you learn in theoretical computer science. Or you might take a course in model checking and learn about Buchi automata. These would be different types of transition systems. So our transition systems are specified using rewrite rules. And you can think of these rewrite rules of expressing how the global state of a distributed system is transformed by one of the different parties, think running a protocol automata, takes a step. So for example, this rule here, it has a left-hand side expressing the precondition for this rule to fire. Here we might have a global state where a key might represent a key input on the network to some agent. So it says if an agent reads a key from the network, gets it as input, and their protocol automata with its thread ID is in step 1, they're in step 1 of their protocol automata, then they can make a step where they output an acknowledgement on the network, and they update their protocol ID step counter from step 1 to step 2, and they record that they've received the key K. That specifies a transition, and these transitions are labeled. So this is called a labeled transition system with an action that expresses what actually happened at a high level. So this might say that a particular thread ID has accepted a key K. Now, a protocol model is specified by a collection of these rules, and that gives rise to a transition system with the trace semantics. So for example, I might have a global state that contains that a key is input to a network and some thread ID TID3 is in step 1. What I can do is I can match that. This is what multi-set rewriting does. I can match that with the left-hand side of this rule, where K gets instantiated with key, thread ID gets instantiated with TID3, and the steps 1 match. So think matching, like if you were applying a rule in a functional programming language or a horn clause in Prolog, think matching. Actually, in Prolog, you'd have unification. So we have a match with the left-hand side of the rule. So we transform our multiset by replacing these two facts in it with the instantiation of the right-hand side of the rule. So we add to our multiset that some agent has output an acknowledgement and advanced his step counter. So this gives rise to a transition from one global state of our system to another global state of our system. And that transition is labeled by the statement that some protocol automata, some thread ID accepted a key. And then, of course, the system can take another step because maybe there are some other rules fire. So we get a sequence of state transitions that are all labeled. And for those of you who have studied model checking and things like that, that sequence of labels we will call a trace. And a protocol will be secure when all traces describing what have happened are good, and there'll be an attack when there are not good traces. And we will be specifying what's good and bad via a specification language interpreted over these traces. I realize that's a bit technical. So how do you specify protocols? So I gave you an example of a rule. There's an example of a rule. In practice, you will have a lot of rules which describe the state automata, the protocol automata of the different participants. So this is actually the protocol automata of the client role in TLS 1.3. So secure socket layer, transport layer security 1.3. And each of these arrows corresponds to a multi-set rewriting rule. And if I give the multi-set rewriting rules for this transition diagram for the client and for the server, I then have a specification of the protocol model. One also specifies the adversary. Typically, one is interested in security against a network adversary who can observe all traffic and record all traffic and can be active and can replay things that he or she has seen and even build things that he or she has seen and use them to replay them into traffic and to try and fool a participant. In addition, one can consider very strong adversaries. The network adversary is very strong. They see everything on the network. But we know that nation-state adversaries are even stronger. They can do things, for example, like corrupt an endpoint. That's how a nation-state adversary will attack your machine. They will corrupt an endpoint, reading keys out of it. And we can even model that with a rule. This rule is sometimes called session reveal or session state reveal. And it says, for example, that if some protocol automata has learned a key, then that key can be output to the network, which means the adversary gets it. It can be given to the adversary. And this might be labeled with session key reveal. Okay, so now we've done two things. We've specified our protocol model via rewrite rules. We've specified the adversary. And now the question is, how do we specify the properties? And here, for those of you who haven't studied logic yet, let me motivate you to study logic. So logic is sometimes seen as a very dry thing. Here we're going to specify security, and this is a very non-dry thing. It's a very interesting thing. The way we might specify, I simplify slightly, that a key is secret would be as a formula in a kind of first-order logic. A first-order logic, for those of you who like technical things, two-sorted with a sort over messages and a sort of time points. And I'll just read you what this formula says. It says for every thread ID, for every key, and for every time point, if some thread ID has accepted the key at time point I, then it's not the case that at another time point, K means the adversary knows or has learned, the adversary has learned that key. So if I complete my protocol automata saying I have a key and I believe it's secret, then the adversary has not learned it. And these formulas are interpreted over traces. So for example, if there is a trace, for my transition system in general, there'll be infinitely many traces where somebody has accepted a key, then it better not be the case that in that trace the adversary has learned the key. If that's never the case, then the protocol satisfies the security property. Okay, so now we've done the three things. We specify the model, we specify the adversary, and we specify properties. And then there are techniques, but they would be techniques for a block course, if I come here and teach a block course on security protocols, for how algorithmically you check this question of does the protocol when run in the adversarial model satisfy the properties. I'm not going to explain that to you, but I'll give you papers at the end that you can consult to find more about it. It's really an exciting question, and there you need topics from theoretical computer science, from automata theory, from logic. It's really a beautiful area because it combines so many fundamental parts of computer science. Now let's completely shift gears. But whenever I talk about specifications and we find an attack, etc., I mean using the techniques that I just showed you. And let me talk about EMV. So this is the global standard for payments. There are now, actually, it's more than 9 million, 10 plus billion credit cards worldwide. So again, I'm talking about these things that you have in your wallet. And it was EMV is Europay, MasterCard, and Visa, but there are other credit card manufacturers, companies like American Express and the like that are involved in EMV. And of course, payments are really security critical. So the standard claims to have the highest possible security. Now, what does that mean, or what should that mean? So low-value purchases don't require a PIN. So suppose I get one of Martin's credit cards because he loses his wallet, so I take a credit card out of it, or if I were a thief, which I'm not, but if I were to pickpocket him and take his wallet, I could get a credit card. Now, what does security mean? Well, I could use Martin's credit card for a low-value purchase. In Switzerland, it used to be 40 franc, and then after Corona, it went up to 80 franc. But I shouldn't be able to do a high-value purchase of like 400 franc, or maybe his credit limit is 10,000 franc. I can't take 10,000 franc out of his account without his PIN. Of course not. Here you have strong authentication, two-factor authentication, something you have, your card, and something you know, the PIN. The PIN is the second factor. But the punchline is going to be the PIN is completely ineffective. The PIN does not work. If I get Martin's credit card, I can withdraw 10,000 franc without his PIN. And that's really, really shocking. The PIN on your credit card is useless. And we find this out not by hacking and playing, but by using theoretical computer science, by using model checkers. So the take-home messages are, I'll describe the first comprehensive model of EMV, and this is a standard running over 2,000 pages of text, directly formalized in this Tamarin model checker that we designed. We found known, and in particular new security issues, PIN useless. We aren't so much interested in breaking systems, we're interested in improving them. So we have a number of fixes for these which are verifiably secure, and we've been working with one of the manufacturers for a new rollout of the credit cards that is verifiably secure. And this experience supports the general hypothesis, don't trust, verify. Formal methods, logic, operational semantics, symbolic reasoning, these are essential tools of computer science, and you need them to build any critical system or indeed any system that you care about. Everything I'm talking about you'll find on the internet. I'm going to show you a little video later. You'll find even more videos of breaking credit cards and things like this. And you'll also find the Tamarin models that we use to find these attacks. Okay, so EMV is a protocol, and it's a beast. 2,000 pages, tons of acronyms, etc. Don't worry, there's not going to be a quiz at the end of this course, at the end of this lecture. I wouldn't dream of that, and I wouldn't dream of trying to explain it to you in detail. But I'd like you to understand at least the main ideas and have a feeling for where problems can come. So it is a three-party protocol in this model here. You have one party is the card, the credit card. Another party is the bank that issued it. For example, in Switzerland, I might use UBS or Credit Suisse to issue my credit card. And then I go to a store. In Switzerland, it might be a co-op, where they have a point-of-sales terminal. And that's the other player in this. I will take my card and I will either put it into the terminal or bring it close to the terminal. Okay? So there are three parties. And how does the protocol look? A protocol is a distributed algorithm, and a cryptographic protocol uses cryptography. At a super high level, first, let me use my little pointer to point. First, the terminal says to the card, it'll say to the card, we're doing a contact or a contactless transaction. The card doesn't know, the terminal has to say if the card's been put in it or not. And then the card will say to the terminal, that's this information here with these application identifiers, this is a Visa card or this is a MasterCard. So the card tells the terminal which one it is. And then the terminal says, oh yeah, I can handle a Visa card, no problem. And then the terminal is going to send things like, we are in Bulgaria, the currency is the leu, I hope I said that right. And the amount of purchase is 10,000. Okay? And then very importantly, and we'll come to this, the card will give the terminal various authentication methods. And there are two things you want to authenticate. You want to authenticate that this is a real MasterCard, in this case here. This is an authentic MasterCard. And you want to authenticate that I am the owner of this MasterCard via a PIN or something else. Two types of authentication: card authentication, cardholder authentication. Then what's interesting, and I have to explain this, even if you don't understand crypto, I think the main idea might be clear. The bank issues the card, so they can share what's listed here as MK for a master key, for which a session key can be generated. So the card and your bank have a pre-established relation, so they can get a shared secret, and they use that to authenticate data using something called a MAC, a message authentication code. So you'll later on see MACs, that's what's going on here. But anybody can make a terminal. There are many terminal manufacturers, and terminal manufacturers have no pre-established relationship with the card. So what are we going to do for secure communication there? We are going to use public key cryptography with a public key infrastructure. And a little known secret, well, it's not really a secret, is that the most successful public key infrastructure in the world is that used in banking. So all of the banks have certificates that say what is their authentic public key, and terminals are able to check these certificates. So quite briefly, what happens here in this step here is this is used, this public key infrastructure is used, and the card sends to the terminal the PAN, which is the card number, and things like the expiration date, and then it sends a certificate that binds the bank's name to the bank's public key signed by the banking certificate authority. So now the terminal can check things signed by the bank. And then the bank is going to sign, this is signing a certificate with its private key, something that binds the public key of the card to the card's name. So in this way, the terminal can get the card's authentic public key, and now they have a way to communicate securely. The terminal, for example, can encrypt things for the card using the bank's public key, and various other data is sent. Okay, that was a little bit technical, but here's the point. There are different secrets shared between different parties, and things will be authenticated in different ways. Between the bank and the card, public key cryptography will be used, but between the card and the terminal, sorry, I said it wrong. Between the bank and the card, symmetric key cryptography will be used, MACs, but between the card and the terminal, public key cryptography will be used, namely public key encryption and signatures. And problems will come in because different parties will authenticate things in different ways to other different parties, and this will lead to confusion. And this confusion will be found by our model checker, and it'll allow us to attack EMV cards. Okay, what comes next is that we have to authenticate that this is a valid credit card. In the old days, only certain static data would be authenticated. So for example, each card would have implanted on it, when it was manufactured, a signed statement by the bank that says this is the card's card number, the expiration date, and something about the authentication procedures that it allows. But that's not very good in practice. Typically, you want to authenticate dynamic data like nonces and purchase and transaction data. So modern authentication for cards uses something called CDA, which is combined dynamic authentication. And we're going to later see CDA is the only thing which is really secure. But that's okay because most of these other authentication methods, SDA and DDA, they're supported by the cards, but they shouldn't be used in practice. Okay, so they have a legacy status. Now something really interesting happens. How do you authenticate me, the cardholder? In some places in the world, you sign some slips, so you use signatures. I was recently in Vietnam, and for strange reasons, you even have to sign things twice. Don't ask me why. There are 4 digital ways of doing it. One is plain text PIN. Plain text PIN is you type your PIN on the terminal. This is where you have your card in the terminal. You type your PIN on the terminal, and it is sent directly to the card. And then the card checks if the PIN is the right PIN, because the card knows the PIN, and sends a yes or a no back to the terminal. Can somebody tell me why this might not be the greatest way to authenticate the cardholder?
Is this yes or no authenticated?
No, it's not. Great.
Or a fake card who always say yes?
Exactly. You can have a card that always say yes, or you can man in the middle and always say yes. Moreover, the PIN isn't even encrypted, so you can steal the PIN as well. So perfect, brilliant, thank you. The next is online enciphered PIN, where we're at least going to encrypt the PIN to the card using the fact that the terminal has the card's public key. But then a yes or no is sent back, and that's not authenticated, so again, that's not really so cool. The next is online PIN. That's where you type the PIN on the terminal. It's sent to the bank. We see that there's all sorts of various options here. The PIN is being sent to the bank, encrypted with the bank's public key, and the bank can check the PIN. We'll see that that's not so bad. Finally, and this is really nice, consumer device authentication. So this is what happens when you use a credit card on your phone using Apple Pay or Google Pay or Samsung Pay. You're authenticated on your device by your face or your fingerprint or a PIN. And then your phone will tell the terminal, communicating over NFC, that you have been authenticated. And this is really convenient. I use this a lot. Okay, so please remember there are different authentication methods. Some of them, as was pointed out, not so great, some of them greater. And finally, at the end of the day, the transaction can be declined or accepted offline by the terminal, or it can be authorized online by the bank. And here what I simply want to indicate is that different data is being sent to the different parties for their decision. The terminal is receiving this SDAD signed data signed with the private key of the card, and the terminal can check that using the public key which was exchanged here. So some things are being sent to the terminal that are signed, whereas the card sends to the bank via the terminal something called AC, which is an authentication cryptogram, and that's a MAC. So again, cryptography is being used in different ways for different parties to authenticate different data, and this might be problematic. Okay, so that was the protocol. So when we do model checking, we have to specify the protocol, the adversary, we'll consider a very powerful adversary, and the properties. So here are some examples of the properties. I won't dwell on the formulas, but if you'd like to, if you've had a course in logic, you might read them. The first says that the bank accepts transactions accepted by the terminal. So here I'll even read part of it. So for every transition and for every time point I, if the terminal accepts a transaction, the terminal says, yes, you can purchase those goods, so the customer gets the goods and walks away with them, right? Then it should not be the case that there's another time point where the bank declines the transaction. So this is how we say that in logic, right? Because that would be terrible if the bank declined the transaction, the store doesn't get the money, but I've walked away with my goods. That would be an attack. So this says that shouldn't happen. So it's not the case that it happens, and then some other cases are covered where some honest party like the bank has been compromised. So it could be that somebody's stolen the bank's key, then things aren't going to work. Now just to recall, this formula here would be interpreted over traces. So if there was a trace where the bank declined and the terminal accepted, that would represent an attack. So this would be, if this was a possible trace of our transition system specifying EMV, that would be an attack. And if there are no such bad attack traces, then we have a verification for our protocol, provided we show that in all of the possible infinitely many behaviors, there cannot be an attack. And that's what Tamarin does. There are two other properties in here. I won't bother to read the formula. One is that the transactions are authenticated to the terminal. So the terminal has two other parties, the card and the bank. So if the terminal says, I think I'm dealing with this card and this bank, and we have a transaction for this amount of currency in Bulgaria, then authentication means that the bank, and if the terminal thinks that, then the bank and the card think the same thing. They see the same thing. They have the same view of the transaction. So it's not like one thinks this is a transaction with one credit card and the other thinks it's with another credit card, or they disagree on the amount purchased. And transactions are authenticated to the banks is the same thing, that the bank's view of what has happened agrees with the terminal and the card. They all agree that it succeeded, or they all agree that it's failed. And when they agree that it succeeded, it's on the same amount, person, etc. Okay, so what actually happens when we try and do the verification? So to make this easier to understand, I'm going to split it up where I consider whether we're talking about contact or contactless. This is first the contact case where you stick your card into the slot in the point of sale terminal. And then I'll consider which way we authenticate that the card is authentic. Remember that CDA is the best. Then which way we authenticate the user. Do we use plain PIN? Do we use enciphered PIN? Do we use customer device authentication? And finally, are we doing this with the PIN online or offline verified? And the properties we check is, first of all, we check that if there is no interference, that everything can execute well and good, and the protocol has the right functional properties if a transaction occurs. We'd certainly expect that. Then we check these three properties that if the terminal accepts and the bank accepts, and the terminal's view and the bank's view of the transaction agree with their partners. And what do we find? First of all, we find that transactions using CDA, this is the strongest way of authenticating my card, and online PIN or no PIN, provided you can recognize my signature, those are secure. We find that if you use plain text PIN or online enciphered PIN, so we find means Tamarin finds, it finds attacks. These attacks are not new. They were known by researchers at Cambridge. They discovered them using their brain, not a model checker, about 12 years ago. And that's the attack that we talked about where you just change a yes into a no. You fake the response from the card to the terminal. If you use these outdated cardholder authentication mechanisms, then Tamarin also finds attacks. And here I'm describing what the attack is. You can modify a cryptogram, and that's not detected by the terminal, so you can walk away with the goods, but only later in the offline case that's detected by the bank. We've also found various issues related to secrecy where you can, for example, read out PINs. Now, this is not something, though, that the credit card companies are going to lose a lot of sleep about because it's not so easy to weaponize. So this is a setup used by the Cambridge researchers. You have to, it's called man in the middle, probably we should say person in the middle or attacker in the middle. The galvanic, the physical connection between the card and the card reader by sticking some sort of a shim in, some sort of a little reader in a reader. And I think if I went to my local co-op with this, and when they give me the payment terminal, I say, excuse me, and I pull this out of a briefcase, they're going to stop me. So this attack would work, but it wouldn't work in practice. Therefore, the credit card companies, which are businesses and want to minimize risk, they're not too worried about this. But the case for contactless is quite different. And what we found in the model that we made, and I'll come back to this, is most MasterCard transactions are secure. So everything lines up, there's complete agreement. But shockingly, most Visa transactions are not secure. And they're not secure because the terminal and the bank can have different views of what's happened than their communication partners, which also include the card. So there can be confusion. Now, why is this so bad? Let's be clear about why confusion can be a bad thing. So this is the problem that Tamarin found. So remember, there are different cardholder verification methods. Do I enter a PIN? Do I use Apple Pay where I'm using the card, the consumer device method, etc. And that information, the protocol, there's some technical terms for it, the CVM is encoded in something called the card transaction qualifiers. And these card transaction qualifiers are authenticated, everything should somehow be authenticated in something called the sign dynamic authentication data. So I've kind of highlighted that in red. Now, protocols often have many different modes and variants and bells and whistles and different ways that they can be executed. And it turns out that in some Visa transactions, in fact in many, the sign dynamic authentication data isn't used, and therefore an attacker can change the CTQ and therefore change the cardholder verification method. And this picture says it all. We're going to have a situation where the card thinks the terminal authenticated me using my PIN, and the terminal thinks I was authenticated using Apple Pay on my phone, that my device authenticated me. Okay, so the fact that this can be checked leads to a confusion where in the end, each party, the card and the terminal, will think I've been authenticated, but I've never been authenticated. So this is this case, I get Martin's credit card, I can use it without any authentication at all, i.e. never entering a PIN. So let's look at how we can do this. So we can take the attack that Tamarin found and we can weaponize it to build a relay architecture attack. Now for this attack, I'm going to use two Android phones. One phone here is going to emulate a point-of-sale terminal. It's going to emulate this terminal on the left-hand side and speak NFC because there's an NFC communication with my card. The other is going to pretend it's my card, and I'm using Apple Pay, and have an NFC connection with the point-of-sales terminal. And these two phones can be under the control of the adversary, and they can communicate with each other over Wi-Fi. And I have two phones because suppose this were Martin's card. What I would do is I would take one phone, one of my Android phones that's malicious, I would put this in my pocket with his card, and I would take the other phone and I would go to a point-of-sale terminal and I'd buy a Ferrari with Martin's car. That's what I would do. Okay, how does that actually work? So the terminal sends the command saying, hey, this is a high-value purchase, we need cardholder verification. It goes to the card, and the card says, yeah, it's a high-value purchase, so you check it online with the PIN. So the PIN should be entered on the terminal. And then the attacker in the relay between the phone on the right and the phone on the left changes what's transmitted to the terminal to say, online PIN is not required because authentication was performed on this device, so it's all good, like I was authenticated with my face. So this data is changed to indicate that I've been authenticated even though I haven't. So let's actually look at this. So here's the setup. The phone on the very right is the phone I would put in my pocket with Martin's credit card. The phone in the middle is the phone I would use to do my Apple Pay. Here I have a SumUp terminal. So for this experiment, we registered ourselves as a vendor with a SumUp terminal, but we later on performed these attacks in stores and things like that with Migros co-op terminals or Schweizer Bundesbahn terminals, etc. But making sure only to defraud ourselves, never to using our own credit cards, never to defraud other people. And this phone here on the left, that's just providing 5G communication. It's providing cellular network communication for the SumUp terminals because the SumUp terminals don't themselves have a SIM card in them. So what we're going to do is we're going to do a high-value purchase. If I recall correctly, it's 400 franc, and we're going to do the man-in-the-middle attack. So here we go. We type 400 franc, no, 200 franc, that's still high value. Then we put the attacker puts the card, the phone over the card, say Martin's credit card, that's in my pocket. Then I take the other to do an Apple Pay, but it's not really Apple Pay, and certain data has been changed, and the payment terminal turns green and says in German, Zahlung genehmigt. That means the payment went through, but there was no authentication. So I don't know how you find this, but this is shocking. This is really shocking. This is a critical system that was designed to be secure, and it fundamentally does not work. And the attack was subtle, and we were able to use these tools and very quickly find them, and not just this one attack, but attack after attack after attack after attack. This is a big deal. There was a lot of media coverage. I didn't find anything in Bulgarian. I'm not sure we searched in the right thing, but I found articles in English, French, German, Chinese, Portuguese, you name it. And it's a big thing because 5+ billion people rely on these, and they fundamentally don't work. And that's shocking. And the situation should not be that way. We're building critical systems. We need mature engineering methods to build them. And one of the points about my research is to build these methods with tools that we can really use. And I think that's one of the, just a footnote, that's one of the exciting things about INSAIT is that there's this foundational focus because there's sometimes nothing as practical as a good theory. You need these theoretical advances to make practice in a very pragmatic way better. So we don't actually like to break things in my group. We like to build secure things. So of course we analyzed the problem. And we found that there was an appropriate way, maybe I won't go into full details because of time, to insist that the card will always supply this static authenticated data and have the terminal check it, and that involved having the terminal, when it sends a particular data package, set a certain bit on something called the TTQ to 1. And this is an easy fix to deploy because you can just update the software on your point-of-sale terminals. You don't have to change 10 billion credit cards in the world. We found actually other attacks as well, and some of them really required changing 10 billion credit cards in the world. Okay, so these were attacks on Visa. And I mentioned that in our first model we found that MasterCard was correct. And then what we thought was secure. And then we thought, okay, now a model is an abstraction of the real world. Did we miss anything? And the real world is a little bit more, so our attacks are real attacks, but maybe we verify things, making certain assumptions about things that we've abstracted away. This sometimes happens in verification. So we said, well, in actual payment networks, there are two banks involved. You have an acquirer bank who's responsible for the terminal, and a card issuer bank who's responsible for my credit card. And there's a payment network connecting them, and actually this payment network isn't just a network, it's a set of networks, a family of networks, one for each type of credit card. And then when we model that, to our utter amazement, we could never have imagined it. You know, you can't make this stuff up. Tamarin found an attack where between the terminal and the acquirer's bank, between the card and the terminal, you change the application identifier such that if you have a MasterCard, you convince the terminal that you're actually paying with a Visa, and then you use the attack we previously discovered on Visa to do a PIN bypass on the Visa, even though the payment is with a MasterCard. It seems crazy that that would work. Tamarin said it would work, we tried it, and it worked. Boom, yet another problem. Yet more press, yet more fixes. So there's this cat and mouse game of attack and defense, but it should not be that way. It should not be that way. We should be building systems that are secure from the ground up by design, not we build them, we put them out, we let them be beta tested, which for an attacker means fundamentally breaking your system, and then we go, oh, we patch them, and then the cycle continues. That is not how we should be building critical systems. After enough of this cycle with one of the card manufacturers, we decided, we enthusiastically came together to build the next generation of payment card protocols, and these will be coming out very, very soon. And I'm very happy that this theoretical work will ultimately touch 10+ billion credit cards. Namely, the credit cards you'll be using will actually come with formal proofs. So I think that's very exciting. Now this pattern of attack and defense, etc., it occurs again and again and again. I won't even go into this slide, but it's just, I want to emphasize sometimes there's nothing as practical as a good theory. I'll say a few words about this slide. We did similar work on the 5G specification, which is being used for all mobile communication, looking at 5G AKA, which is authenticated key agreement used to authenticate the different parties. As you can imagine, we found attacks. So for example, I can make phone calls with my phone, but have the calls charged to Martin. Sorry, Martin, I don't mean to pick on you. First, I do fraud on your card, then I do fraud on your phone. And again, the problem, they were often very, very subtle. it had to do with the fact that protocols are developed as an art rather than a science, and we need better ways. Okay, let's draw some conclusion. Formal methods, symbolic reasoning, logic, semantics, these things really matter. You can, believe it or not, rob the bank with automated reasoning using a theorem-proving tool. These formal advances, so working on theory, have brought tools to the point where they can be used and should be used. And this is really good hygiene. When you design a system, not just a protocol, you should be clear about what that system should achieve. You should be carrying out proofs. You should be following standardization efforts. As a protocol like TLS is standardized, it goes through many, many revisions. With each revision, they should come with formal proofs. And the good thing is these tools like Tamarin are now advanced enough that you can actually do that. There are two challenges. One, complexity. We're up against very hard problems. For those of you who know about things like state explosion problems and undecidable problems, etc., we are up against these. You can't get around undecidability. But we work to make our tools more powerful and easier to use and easier to interact with. But this is a very challenging problem. It's also the case for program verification. And the halting problem is undecidable, but still you can prove many programs terminate. So the question is, how do you build powerful methods for doing that? Another point is education. And as I mentioned, it's important to have an education of formal methods, semantics, logic, and security. So one of the things I'm doing at ETH is educating students in that, and I hope also to contribute here at INSAIT into the education in these areas, because these are really fundamental skills for building practical, impactful applications. So critical systems require a firm educational basis. Let me just conclude with some papers you might read if you're interested in learning more about the topic. Most of what I talked about came from a paper at Oakland Security and Privacy in 2021. So I consider myself to be somebody who works mostly on theoretical problems, and then I try and apply them. But interestingly enough, this won the Best Practical Paper Award of the conference. So Oakland is really a top security conference, and I was really happy to win a Best Practical Paper Award. Again, sometimes nothing is as practical as a good theory. And we kept finding more and more attacks, and you'll find some of the attacks in papers that have been published or papers that will be published. And below I have some papers on the theory. One thing I want to point out is that the original work on this actually started about 12 years ago, with the theory publications coming out 10 years ago. For those of you who are looking forward to seeing theory moving into practice, it happens, it's real, but it does take time. You really have to first work on improving the foundations and building methods on top of them, and then building tools, and then training people to use the tools and applying them. It's a process that takes time, but it's immensely rewarding, and I encourage you to take advantage of these possibilities here at INSAIT. Thank you.